So welcome to everyone. I'm going to try to arrange this so I can see um, more of you. Okay. Now we do have people from different places and around the world, different time zones, etc. I realize that I will try to avoid idioms, but if there's something I say that seems like an idiom that you don't understand, please ask. If you find that I have an accent that in some way is hard to understand, don't be shy about asking on that. I see there's a chat, all right? So got a couple. All right, all right. Um, I think the easiest thing for me to spot for questions is if you just use that symbol that I believe you should have access to. Let me see if we have that down here. Do you have access to a little hand, raised hand symbol on yours? Yes. Okay. Okay, great. So if you use that, I think the chances of me spotting it are much greater than if it appears in the chat. So if you don't mind doing that, please do that if you have a question. Plus, please ask a question. I'm happy to answer questions. My experience has been that if you have a question, somebody out there has a question, it's likely there's a bunch of people, or at least several people, that have a similar question. So don't be shy about asking questions on this. Other than that, we will follow the same schedule for the 3 days where you have the 10 to 12:30 p.m. That's New York time. I know we have a lot of different time zones here, but New York time. So 2.5 hours in the what is our morning, and then we have the 1:30 to 3:30 in the morning. I will put a break in there because I think it's kind of hard to go a full 2.5 hours, but it'll be a brief break, 10 minutes, and I'll try to stick to that pretty sharply. So I'll ask people to come back at that point. The largest break we have is that 1 hour break between what is our morning and afternoon session here. Um, and you should have at this time received the files in advance that have the Lavaan and the M plus code, for this, as well as the main data set that we'll be using to illustrate things. So are there any other questions before we just get into the lecture material? All right, I'm not seeing anything there. All right, then let's get going then. This is an overview of what we will be talking about. First thing I'm going to do is review longitudinal models that are out there. Autoregressive growth curve, fixed and random effects, and some of the hybrid models that are combinations of these different more classic models. And when I present these longitudinal models, I'm going to present them in at least a couple of different ways. One way is I'm going to give a path diagram of it. I know that just by hearing your background that a number of you have some experience with path diagrams, but I don't think everybody has. So I will define those symbols, what they mean. And of course, feel free to ask questions if you have questions on those. I'll give the equations that correspond to the path diagrams. So the equations are going to be the same model, just represented in equations rather than a picture. And then I'll give you the Lavaan input and the Lavaan output, which would be very similar to what it looks like in M+. You should be able to find the same statistics. And if there's any issue with that, I'm happy to go over that as well with the questions. All right, so then here's the part I was talking about: reviewing, present the longitudinal models, both the input and output, and then estimation and interpretation. We're going to take a little bit more time on that and talk about how to estimate and interpret each of these models that we go over in the first part. in even more detail, talk about the fit of the models, choosing between models, and then what happens if you have more than one series of repeated measures? How do you analyze those? So, starting point, a number of you will already know this, but just to make sure we're on the same page and using the same language, by longitudinal models, we're talking about tracking the same cases over time. These cases can be individuals, they could be counties or nations, any unit of analysis that is tracked over time. And when we talk about tracking them over time, we'll talk about how many waves of data we have. And all that term waves mean is the data at each time point. So if we say we have a 3-wave study, that just means we collected data at 3 different points in time. The waves can be equally spaced. So maybe you have data that's being collected every month, every year, or they can be unequally spaced. So maybe for funding or other reasons, the first 2 waves of data are separated by a year, but then they had to wait 2 years or 3 years to go to the next wave of data. Also, the number of cases with longitudinal data generally greatly exceeds the number of time points. So with longitudinal data, it's not unusual to have maybe a couple of thousand cases tracked over maybe 5, 6, 7, 8, 9 waves, something like that. If you have a situation where you have a fairly small number of individuals, but you track them over a long period of time, that's more likely to be treated as a time series analysis rather than a longitudinal. So there's not any rigid definition that separates having multiple time series from longitudinal data. It just seems to be the case that if we have many more cases than time points, people refer to that as longitudinal data. There also are 2 formats in which data might be collected or presented. One is called the long format. And what this does is it stacks the observations and how many times they're observed over time, and then moves to the next person and gets how many their over time observations on whatever the variable is. So I have a hypothetical example here where suppose we're interested in whether the number of hours studying makes a difference in the grade point average of an individual. So here we have for these data, we have 3 ways for person 1, and we're observed this person at time period 1, 2, and 3. For the hours studied, it's 2, 4, and 4. Their GPA is 2.8, 3.1, 3.2. Then we go to the second person, and we have 3 observations for that person, and we have their hours of studying and their GPA, third person, et cetera, et cetera. These data are described as being in the long format. There also is what's called the wide format. And with the wide format, now we just have each row corresponding to a person, and then we create a new variable for each time period we observe that person on a particular variable. So this is the same data set now rearranged in the wide format. We have person 1, the first time they're observed, their hours studying, that's a new variable now. And then the second time period where we observe how many hours they study, that's another new variable. And the third, and then GPA at time 1, GPA at time 2, and time 3, right? These are new variables in this wide format. And then we go to the second person. And this person also has 3 variables for hours studied and 3 variables for GPA. This workshop, we're largely going to be using this wide format. We're arranging the data in this wide format. Any questions on that? This difference between the long and the wide? There are some, most of the statistical packages now have options for that where they can convert your data from one to the other. Yes, Aaron.
Yeah, I have worked mostly with long format in the past because I work a lot with ragged data sets where we've got, maybe two observations for someone and seven observations for someone else.
Yes.
Um, uh, will any of the problems that we talk about in this course have uneven follow-up in this way?
We can handle it by just coding those ones as missing. So suppose, let's take this example that's on the current slide. And let's suppose that for person one, we didn't have time period 2 hours studied. We would just put in a missing code there.
Great, thanks.
Yeah. And we would do the same thing for any kind of time where you have that uneven time setup. Any other questions? And the way you would handle that with the missing data, with these SEM approaches, SEM packages, there's a very nice set of features that's sometimes called full information maximum likelihood or direct maximum likelihood or case-wise maximum likelihood. All of them boil down to the same thing. It's an approach to missing data where you just take whatever information on whatever variables is available for each person and you estimate your maximum likelihood procedures using that information. But if you're somebody who's more familiar with multiple imputation, you could do that too, and just combine that information with multiple imputation. The advantage of this FIML, full information maximum likelihood or direct maximum likelihood, and the multiple imputation is that they make less restrictive assumptions on the nature of the missing data. So if you've looked at this missing data, there are these horrible terms, missing completely at random, missing not at random. Missing completely at random is saying that there's absolutely no patterning to the missing data. Missing at random allows the missingness to be related to variables that are observed in your data set. That's less restrictive than the missing completely at random. And fortunately, the multiple imputation and these maximum likelihood approaches work under that less restrictive assumption of missing at random. And those options for missing data are available both in Lavaan and M+, and most of the SEM packages. Okay. Now let's also clarify the type of longitudinal variables. There are time invariant variables. And as the name suggests, these are variables that do not change values for a given individual during the period of the study. So if you had assigned sex at birth, right? Someone may change their gender identity. I'm not talking about that. I'm talking about the assigned sex at birth. That's not changing over the period of observation. Race and ethnicity, place of birth, age at which a person entered kindergarten, variables that have not changed for a given individual over the period of study. This does not mean that it doesn't vary over individuals. Of course, these are variables that can well and do vary over individuals, but for a given individual, they're not changing over time. Sometimes this is confused and suggested that these are variables that cannot change over time. And really, I think all our properties will hold as long as over the period of study that you're undertaking, the variables you're declaring as time invariant, they've not changed for the individuals, each individual over time. So, for example, one of the data sets sometimes used has a variable which is like completed education by age 20 or something like that. Well, education can change over time, but if you have a variable like completed education and you're getting these people that are already through with their education, it's behaving like a time invariant variable, and you could treat it as such in a study, in an analysis. Time varying variables, right? These are variables that change values during the period of the study. Now, again, a tricky part of this one, this is not saying that all cases must change values. It's just saying that for at least some of the cases, and usually a significant proportion of the cases, they change their value from one wave of the data to another. Here, examples of this would be things like income. You're doing a study of mood, or you're looking at families and the number of children in the family, job status, blood pressure, if you're doing a more medical type study. These are time varying variables for an analysis. I think those distinctions are clear, but if there's some ambiguity and you have a question, don't hesitate. Yes.
Could you explain the cannot change versus do not change again for the variables?
Yes, do not change. So let's say that we're looking at a study and we have as a covariate something like the education of a person. And in the population you're looking at 40-year-olds, you're looking at an elderly population. Theoretically, yes, it's possible. They may change their years of education. But for most samples, we would expect the years of education to be a time invariant variable throughout that study. And so we could treat it as such. Does that answer your question?
Yes, thanks.
Rosa?
So I think I have the same question because I see in some previous studies, they use the average values of time varying variables and treat them as invariant variables. So I'm not sure how can we explain that we can treat like the average values of time varying variables and invariant variables in our model.
That's a good question. So if it would depend on how they're using that average value. Like if they're subtracting out that average value, that's like an estimation type routine, that they're correcting for. But if they're treating the average value so that they can treat it like a time invariant variable, that might be something a little different. That's assuming that the effect of that variable is the same over time on whatever outcome it's influencing.
Yeah.
So I'd have you'd have to know the details of how the authors are using it to see whether that works.
Because I don't see any explanation, right? So because they treat some variables and time varying variables, and then they treat some time varying variables and use the average values as time invariant variables, and they see them as the moderators for the trend, right? Because we have because I don't see any explanation about that in the paper. So I just wonder how how can we treat time varying variables differently in one model?
Yeah, I would say that if the variables are really time varying in terms of what their effects are on whatever outcomes you're looking at, I generally would want to treat them like that. But I'm also recognizing that sometimes in order to estimate the model, people are using the averages of the time varying variables and maybe deviating away from that. And if that's what those authors are doing, then there could be a rationale for
Mm-hmm. Yeah, thank you.
it. Scott.
So, I'm not sure how this would work with longitudinal, but there are some variables, personality or some others that researchers have developed that are assumed not to change. We know they do change, but could you model that as time invariant whether it's a control or not, or would you have to have that as a repeated measures?
Yeah, that's a great question because, as it's not my area of expertise, but as I understand it, there is some research. Personality used to be viewed as extremely stable, but there's more research coming out suggesting that there are some fluctuations in it. It would depend on the reviewer, right? I mean, if you could say, you could describe it as such. You could just say, for my purposes, for this period of time, there's a research that suggests it's relatively stable, so I'm going to treat it like a time invariant variable. So the way I would say, Scott, is it's like you'd have to make a substantive justification for it.
Right. No, I appreciate that. I mean, there's a number of variables besides personality that are treated that way. But you're making a big assumption, but it might be relevant in I think in some cases to model that.
I agree. If I'm assuming the worst case scenario, I guess maybe I'm too pessimistic, but suppose they just, because of economic considerations, maybe they just measured personality for the first wave and just assumed it was relatively stable, and I don't have the personality measures over time. I could see that I would present it as a limitation of the study, but it's better to have it in there, at least at one time period, than not at all if it's an important characteristic for the outcome.
Thanks.
Sure. Okay. All right, so this is about choosing longitudinal models. Now, what you'll get, and this always frustrated me endlessly, to this day it frustrates me, is people would say, well, you should just use theory and your substantive expertise to choose your longitudinal model. I'd love to, but in so many of the areas that I work, they're not that specific. And I'd love to hear about it if you're working in an area that's so specific and it tells you exactly what type of change, longitudinal change to expect, and the corresponding model to that. In reality, what happens is that theory and substantive literature is lacking the guidance. You're pretty much on your own. Rather than that, the model choice is based on, well, what are other people doing in the area who have modeled this? Or what are the fads? What's the latest? What type of methods are people using and saying this is the up and coming, you always should use this type of approach? And then, of course, there's software availability and what you're familiar with. In reality, these are the factors that influence what longitudinal models people use. Now, is that a problem? Well, let's think about scientific research, which, based on your brief introductions, it sounds like all of you are engaged and have as an ideal scientific research. Suppose your goal is descriptive. You really want to give a great description of whatever the outcomes are that you're looking at and how they might relate to another variable or two. Well, if you've got the wrong longitudinal model, you're going to undermine that goal of a scientific description of whatever it is you're studying. Or let's say that you're testing a theory. There's a theory suggesting that this variable X will influence this variable Y, or that this drug will have this impact. Well, if you've got the wrong longitudinal model, that means that there's other terms out there that are influencing the outcome that you have in the model in the wrong way, or maybe don't even have in the model. And if that's associated with those key variables that you're trying to do your theory testing or hypothesis testing with, it's going to be wrong. Closely related are causal inferences. You want to make a causal inference of how one variable affects another. You got the wrong longitudinal model. You could have confounders out there terms that you left out that are in the correct longitudinal model, but aren't in the longitudinal model you happen to choose. And then finally, predictions. If you have as a scientific purpose good predictions, again, if you have the wrong longitudinal model, you may not have the ideal predictions for your model. So, the way I see it, if you care about doing scientific research, you should care about what is the best longitudinal model to use. What's most appropriate for your data. So here's what we're going to look at. I mentioned this briefly in the outline, but here's a little bit more detail on it. We're going to look at a series of classic models, widely used models for repeated measures. We're then going to look at some hybrid models, which are newer, and some of them, the alt ones being used a fair amount. Talk about model estimation and fit. How do we compare across these models in order to select from among the different ones? And then how do we extend this when we have multiple repeated measures? So before I start with the first classic model, any questions on what I've gone over so far? Okay. All right, so what I'm going to do now is I'm going to go over some well-known, widely used models for longitudinal data. Try to give you a sense of them, how to interpret them, how to represent them in both path diagrams as well as in equations. And at the top of my list here are autoregressive models. This is when you have one repeated measure, and I'm using that term repeated measure just to refer to the same outcome variable that is observed in a longitudinal study over time. So you're observing this repeatedly. And this autoregressive model is just based on this common idea that the best predictor of a variable's value today is what it was yesterday. This, in a sense, captures a type of inertia where variables exhibit a partial dependence on their prior value. And here we can just think of so many things in life or in studies that we're doing that exhibit this type of behavior. If you're an economist or a sociologist studying a person's income at time t, boy, usually income at time t minus 1, the time before, is going to be an excellent predictor of what the current income is. Or if you're a psychologist doing a study of mood, have people keeping diaries on their moods. Well, what their mood was an hour ago, probably going to be a pretty good predictor of what their mood is right now. A political scientist looking at presidential approval. Look at what it was in the prior month. That's probably going to be a nice explanatory variable for current presidential approval. On and on and on. I think that you all have different areas in which you're working, and I don't think it's hard to come up with a justification for why a prior value will be a pretty good predictor of the current value. Now, we can represent this in a path diagram. So let me explain some of the basic symbols in the path diagram as I will be using them. Most of you probably know this, but path diagrams are they're over 100 years old. The symbols and the conventions on the symbols have changed a little bit, but the basic idea of using these arrowed figures comes from a Sewell Wright, and he first developed this in 1918, 1920, in that period. And it has spread to many disciplines now. Some of you may be familiar with DAGs, directed acyclic graphs. And when you see these, you may think, well, the path diagram is the same as DAGs. they're a little bit different in that the path diagrams generally are representing relationships that are linear in the parameters, whereas the DAGs are non-parametric. They're not specifying an explicit functional form. We'll see this when we see the equation representation of this. Just out of curiosity, if you could put a thumbs up or something, how many are familiar with DAGs? Yeah. Okay. All right. All right. And now, how many are familiar with path diagrams? Okay. All right. Not so interesting. So not everybody for the path diagram. So let me just take a moment just to talk about it. So in a path diagram, if you have a box, this is an observed variable that's in your data set. Right? Boxes enclosing a variable represent observed variables that are in your data set. The single-headed straight arrow, this is representing an effect from the variable at the base of the arrow on the variable at the head of the arrow. So in this path diagram, y1 is determining, at least partially, y2. y1's affecting y2. The error terms are not enclosed in a box or anything else. So the error terms in this diagram are epsilon 1, epsilon 2, epsilon 3, etc. right here. So I think those are the key definitions there. Now, this slide is just showing the equation beneath the path diagram that corresponds to this diagram. Right? They're providing the same information. But let's go over these equation terms that correspond to the path diagram. YIT, this is the outcome variable. Y is the outcome variable. I is going to index the cases in the sample. I runs from 1, 2, 3, all the way up to n individuals, the most common situation, n individuals in the sample. So when you see the yi, that means that the variable can vary over cases. The t refers to the time period or the wave of the data. So YIT means the value of y for the ith person at the tth time period. Let's move over now to alpha. Alpha t is an intercept. This is just like, it is a regression intercept. It's the value you expect the dependent variable to take if the explanatory variable is 0, right? Alpha t is the value that the expected value of YIT when YIT minus 1 is 0. Regression intercept. This rho sub t, t minus 1, this is the autoregressive coefficient. It is a regression coefficient. It says if the prior value of y, that is YIT minus 1, if the prior value of y shifts by 1 unit, we expect YIT to shift by rho units. It tells you how much we expect the dependent variable to shift for 1 unit difference in this explanatory variable, which happens to be the lag value of the y variable. Epsilon IT, this is the error term for the ith person at the t time period. This equation is the same as the path diagram. The path diagram, as is common, does not often represent, it doesn't put in the I index, like the I here. So the 1, 2, 3, 4, 5, this represents the value of t. Y at the first time period, Y at the second, third, fourth, and fifth time period. Now, assumptions. What assumptions are we making? Well, we make the usual regression assumptions. We assume that the expected value of the error term is 0 at each wave. So epsilon 1 has a mean of 0, epsilon 2 has a mean of 0, all the way up to epsilon 5. And the covariance of yt minus 1 with epsilon t is equal to 0. So this error term here is uncorrelated with y4. This error term here is uncorrelated with y3. That's what this assumption is telling us. These are some of the basic definitions of the path diagrams. I'm showing you the equation that is just another way of representing the path diagram. If you have questions on either, please ask it right now so we can, just keep all this straight to start with. Any questions on either this path diagram or this equation, which is representing the autoregressive model? Yeah, Steve.
Yeah, I was wondering if you could give an example or tell us when an autoregressive model wouldn't be appropriate. Like, isn't the previous value always a good predictor of the current value?
Yeah, that's a great question. Growth curve models, which we're going to go over, is an example. In growth curve models, you assume that there are individual specific trajectories and that the people have different starting points and different rates of change. And that's all you need to explain the data. In fact, in the 80s, Ragosa was a psychologist, psychometrician, and he was criticizing the use of autoregressive models. He was saying you really should just be using growth curve models. What's really going on is you have individuals with different starting points and individuals with different rates of change, and people are fitting autoregressive models to this, and that's incorrect. That's not an accurate representation.
Thank you.
Sure. Any other questions? Okay. This is just giving more details, repeating some of the things I said, just so that you have it in your notes on that equation. Now let's jump to this running empirical example we'll be using. This is an example where the outcome variable is the log of hourly wages. It's a sample of 545 men. This is working males was a sample, full-time working males who completed education by 1980. It's taken from this well-known longitudinal data set, the National Longitudinal Study of Youth. And it's a data set that methodologists have tortured over the years. I mean, so many people have used this data set. And since it's so well known, that's part of the reasons that I chose this, plus it's in a well-known data set. And we'll see that some of the models we fit are having better fit than some of the ones that were from methodological articles that use this. I'm going to start with the autoregressive model. I'll talk a little bit about the Lavaan input code and output and interpretation of the results for this one repeated measure. All right, so this is what the Lavaan input would look like. Library Lavaan just says you would have already downloaded and installed Lavaan. This just says pull this into the active core for me, the Lavaan, and then you're going to load the data. And so this is just the data set that's going to be analyzed. It has a header, etc. This is just giving a title to this run. So the pound sign is enabling you to put comments in here to remind you later what you're doing. So model 1, unconditional autoregressive. And in Lavaan, we're going to assign to this term model.1.ar. This is model 1 autoregressive. That's the reminder for me. I'm going to assign to that term all of these commands that come afterwards. So every time I say model.1.ar, all these commands are going to come along with it. This is just a way that I can run this model with a short notation. And this is showing you how to build what is in essence like a measurement model. This log wage 80, this is the natural log of the hourly wage in the 1980. Same convention for the remaining log wage variables. And this log wage, this is regress on 1. All this is doing is this is how you're getting the intercept term. You know, some of you probably have seen matrix algebra presented presentations of multiple regression. And if you have seen it, you've seen in the X matrix a column of ones. This, in essence, is just doing that. It's regressing log wages on the constant 1 so that it can get an intercept. And we'll see how the lagged relationships also enter this. But this is how you can get intercepts using Lavaan. Just regress your outcome variable on the constant 1. This tilde sign you can interpret as regress on. So this says regress log wage 80 on the constant 1. But regress log wage 81 on the constant 1, etc. Down here, the double tilde. This is standing for covariances. So this is log wages now, 80 through 87. These are the outcome variables. So when you say log wage 80, double tilde log wage 80, that's saying give me the covariance of these two variables. The covariance of a variable with itself is just the variance. So this is really just requesting the variance for log wage 80. Log wage 81, again, it's going to be the variance of the variable all the way down here. So the double tilde is the covariance, requesting the covariance. Here's the real autoregressive part. Log wage 81, remember I said tilde stands for regress on? Log wage 81 regressed on rho. This is the name we're giving to the autoregressive parameter. You know, this is, let's go back to the equation. Right here. The rho. Regress log wage 81. Assign the coefficient the name of rho. And regress it on log wage 80. There's the lagged relationship. Log wage 82 regressed on rho log wage 81. Notice that I give the same name for the coefficient rho here. What? Any guesses on what that's doing?
It's constraining the autoregressive path to be the same across time.
Exactly. Thank you, Ryan. Yes, that's the way you can introduce equality constraint. You name the parameter and give the same name to all the parameters you want to make the same value. Remember, it's going to estimate what the value is. But it says, look, you estimated these autoregressive coefficients in all these relationships. You estimate it, but keep it the same value. So it's not giving you the specific numerical value. It's not saying make this 0.3. It's just saying whatever you estimate it, give it the same value for all these autoregressive relations. This single quote here, right here, that's saying, okay, we're done with this model. Here's that single quote right up here again. And this little left arrow with the dash, this is saying every time you see model.1.ar, include all these commands up until this point where I stop you with this single quote. To fit the model with Lavaan, there's this fit command, fit.m1. So assign the results for model 1, the fit of model 1, to the output of running this command, sem model.1.ar. Well, where did we see that before? Well, that's right here, model.1.ar. Data equals data. Well, right here, we assigned the data from this Halaby2.dat to data. We just called it data, not very original, but it's reading in that data. And then the summary statistics we want from that, right? From fit.m1, put in there, fit measures true, standardized results true, R-square true, we want those. And this is just capturing the output in an output.txt file that we'll see momentarily. So this is a first exposure. You're going to see it multiple times with different models, but that's the first exposure in Lavaan. And here's what the results look like. So the result of regressing log wage 81 on log wage 80, 0.623, it has a standard error of 0.012. Its z-value, the ratio of that estimate to its standard error, is really large, 52, highly significant. And if you standardize it, it comes out to a standardized coefficient of 0.582. Unstandardized, it's 0.623. And remember, it's the same value for each of these auto regressions that we've run because we have that equality constraint. We call them all rho, which makes them an equal in value. So what this says is if I increase a 1 unit difference in the log wage 80 leads to a 0.62 unit difference in log wage 81. Same interpretation for the other autoregressive relationships here. This last column here is for standardized coefficients. So this is in standard deviation units. First column is in log dollars units. Any questions on this output? I apologize that the heading is a little bit misaligned. It had to do with translating, copying, and pasting. But any questions on that? I want to make sure everybody understands that output. Rosa.
So I have a question. So let's assume that an event happened at, for example, time 4. So we can argue that the autoregressive coefficient may be different from time 4 to time 7. So do we need to change the constraint in our model?
Yeah, that's a good question. It could be that one of your hypotheses is that there was some major intervention. We've all been through the pandemic. Maybe the pandemic changed the nature of this autoregressive relationship, and you wanted to test that. Well, you could just remove that constraint in that pandemic and beyond period, and see how well your model fits. If you force the autoregressive coefficient to be the same over time versus allowing it to be a pre and post pandemic. And if your model fit improvement is significant when you allow them to differ, that's evidence supporting this idea that the pandemic shifted this relationship. So by all means, yes, if you have good reasons to suspect it's part of your hypotheses, or if you even wanted to test this, whether this equality constraint is a good idea, you can do that. But good question.
Thank you. Yeah, thanks.
Yes.
Hi. So is there any easy way to constrain the standardized estimates rather than the non-standardized estimates?
In
And is
some
it common to
packages
do
you
that?
could, you're right, you said easy. In some packages there are, but let me question the justification for doing that. Standardized, if you want to compare over time, if you want to compare across different groups or individuals, most people would argue that standardized coefficients are not good for that. Because what happens is that individuals or groups or time periods can differ solely because of standard deviations. So their unstandardized coefficients may be the same. But if their standard deviations shift, that could lead to a shift in their standardized coefficients. And so forcing them to be equal really may be misleading, because they may be equal in their unstandardized coefficient, and the only reason they differ in their standardized is a shift in the standard deviation. So theoretically, it is possible, but it might not be for many applications that I can think of. It's probably not going to be a good idea.
So I didn't think I understood the reasoning very well. So you said that for standardized coefficients, essentially we are constraining the standard deviation to be equal across all our samples, right?
No, I said that if
For
you
the data.
apply the standardized coefficient. Here, let me give you with this example. Let me just make up something here. Suppose that the unstandardized coefficients are the same from 81 to 82 and 82 to 83. So 0.623, that's right. That's a good estimate. But let's suppose that in this 1982 period, we had a recession, and this led to much bigger standard deviations in the log wages in 83. Well, if you were testing the equality of the standardized coefficients, you say, oh, look, they're not the same. But the only reason they differed was because of the standard deviation shifting on the log wage variable. The unstandardized coefficient, the fundamental relationship is the same. It's just that the recession led to much difference in standard deviation. And you're mistakenly thinking that this fundamental relationship has changed over time. Does that help at all?
Yes. Okay. Yeah, that's helpful. So essentially, does that mean that in longitudinal data analysis, we shouldn't standardize the data generally?
Yes, most definitely don't.
Okay.
Yeah, don't standardize it. See, we can get standardized results from the unstandardized coefficients and the standard deviation of the variables, but we can't go in reverse. If the only thing we have are standardized coefficients, we can't get the unstandardized.
Right.
So a more complete analysis is having both the unstandardized and the standardized.
Thanks. That was really helpful.
Sure. Okay. I'm not seeing any other hands. Rosa, yeah.
Yeah, so I have a question. So if the distance from like 80 to 81 is not equal to the distance from 81 to 82, so do we need to free the autoregressive regressions in our model? And the second question is about just the first thing that we regress the weight on the constant one. So I wonder, so if we don't do that, will it affect our model fits, or it just help us to get the intercept in the outputs?
Yes, you could affect. All right, so let me. So suppose you have unequal sized waves. This, I think, this is what you're asking, Rosa, but correct me if I'm wrong. if you have unequal size distances between your waves of data, this equality constraint may not make sense because maybe it was a 1-year interval for wave 1 and 2, and it's a 3-year interval for wave 2 and 3. So you would want to remove that equality constraint that assumes that you have equal type waves, and you can do that.
Yeah.
There's no problem with doing that.
Yeah.
With regard to the intercept, here are the intercepts of the
Yes.
output. And so you can get the intercepts, that little dot there. Notice that all of these log wage variables have a dot except for the first wave. Well, the first wave, the intercept is really just the mean of log wage 80. That's the first time period that wages appears. And it's just taking the mean value because there's no lag value that's influencing it. The other ones are the intercepts, like from regressions, because we have a regression equation for 81, 82, 83, et cetera. And these are giving that. Now, your question was, do we have to put that in? Unless you're using deviation scores, unless you're subtracting out the mean of the variables, yeah, you got to put them in, because if you don't, you're saying, when you do your modeling, you're saying that the intercept is 0 for those relationships. And you can see not all these intercepts are 0, right? They're significantly different from 0. And if you force them to be 0, they may influence the regression coefficient you get out.
Yeah. Yeah.
So the
Yeah,
general
thank
rule
you.
would be put it in unless you've got really good reasons not to.
Yeah.
I mean, you don't have to
Yeah.
necessarily give it a lot of interpretation, but put it in to get your regression coefficients right.
Thanks.
So I'm continuing down the output from the same autoregressive example. And notice this dot again. It doesn't appear for log wage 80, but it appears for all the other ones. Again, log wage 80 is the first wave of data we're observing, so there's no lag value influencing it. So this is the actual variance of log wage, 0.310. The dot log wage 80, the dot means that these are error variances. Right? This is a little confusing. Both in M+ and in Lavaan, the dot log wage here, 81, this is the error variance, the unexplained variance in 81 when you regress it on the log wage 80. And the 82, the 0.155, this is the unexplained error variance when it's regressed on 81. So it is an error variance if you're talking about an outcome variable that has explanatory variables. It is the actual variance of the variable if it is an exogenous variable. Have you heard that term exogenous? I'm not sure everybody here has because of the different backgrounds. Exogenous just means you got a variable that's not influenced by any other variable in the system. That's a simple definition of it. The exogenous variable. The exogenous variables in your model, you'll get variance estimates of them. If it's an endogenous variable, END, endogenous variable, these are variables that appear as a dependent variable, at least somewhere in the system. And if it's an endogenous variable, these variances are error variances in the model. Now, it's not surprising all of these are significantly different from 0. If they weren't significantly different from 0, we'd be explaining all the variance in the outcome variable. And that would be pretty highly unusual for that to happen. We also requested the R-squares, and we can see the R-squares for these autoregressive models. And as things go, considering we only have the lag value of the variable as an explanatory variable, these are okay. 30% of the variance in log 81 is explained by 1980, about 47% in 82 explained by 81, 48%, etc. Any questions on this output I've just gone over with the autoregressive model? Okay. Why is there not an R squared for log wage 80? Anybody?
It's an exogenous variable, so nothing's explaining it in the model.
Exactly. It has no predictors, so there's no R squared to be had. Good, thank you.